All right, everybody, welcome back. Today what we are going to do is we are going to try to find the roots of polynomial functions, and we are going to use what we call the rational root theorem. All right, so for this first one, it says find the roots of h of x equals x to the third power minus 8x squared plus 19x minus 12. So typically what I would try to do is I would try to factor first. It's something we're pretty comfortable with, and if we can do it, it should allow us to find multiple roots at the same time. So if we're doing this, I would group my first two terms together and divide out what they have in common. But kind of already looking at it, I can see that there's no way the second grouping is going to end up looking the same. So for example, if I divided out an x squared for my first group, I'd be left with x minus 8. And then in my second group, they only have 1 in common, so then I'd be left with 19x minus 12. And since the inside of our parentheses here are not the same, that means we cannot factor this by grouping. So I'm going to erase this, and we are going to kind of start from the beginning. So this is when the rational root theorem is beneficial for us. The rational root theorem says if a polynomial has a root, a real rational root, it will be from our p over q values. What that means is we need to take our constant at the end, that is going to be our p-value, and I am going to list out the factors of 12. Those factors are 1, 2, 3, 4, 6, and 12. And then I'm going to take what we call our q value, which is our leading coefficient, and in this case it is just 1. So I need to create a list of values, and that list of values is going to be all of the factors of p divided by all of the factors of q. So it's going to be positives and negatives. It will be 1 over 1, 2 over 1, 3 over 1, 4 over 1, 6 over 1, and then 12 over 1. Luckily for us, our q value is just 1, so there aren't other factors for us to do, but we will take a look at what that would look like in our following problem. So I have my list of positive and negative 1, positive and negative 2, positive and negative 3, positive and negative 4, positive and negative 6, and then positive and negative 12. So the rational root theorem says if this polynomial does have any real rational roots, they are going to be from this list. Well, what I could do is I could just start picking values from here and trying to determine if something is going to be a factor or not. Well, let's use some of our previous concepts from before. We know if we do synthetic division and our remainder is 0, that means something is going to lead us to a factor. So what I would do is start with positive 1. So I'm going to divide our polynomial, our original polynomial, using synthetic division by 1. So really what I'm doing is I am dividing this original by what would become x minus 1 as a factor. That's what I'm doing right here. All right, so I'm trying to see if x minus 1 is a factor by determining if 1 is a root. All right, and what we're going to have to look at is the remainder. So now if I do this, I'm just going to quickly do my synthetic division. We drop the first value, and then we are going to multiply on the outside and add on the inside. Multiply on the outside, and then add on the inside. Now, if I do this, I end up with a remainder of 0. So what that tells me is x minus 1 is a factor because x equals 1 is a root. All right, so essentially the idea here is if I take x to the third minus 8x squared plus 19x minus 12, and I divide by x minus 1, I will get this polynomial over here, which is an x squared minus 7x plus 12. With no remainder, that means it goes in evenly. All right, so we're kind of getting off on the right foot here. We know one of our factors. Well, we got to find the other ones. And so the rational root theorem says that if there is any good roots, nice rational roots, they are going to be in this list. But that doesn't mean everything in that list is going to be a factor. But since I found one that works, what I can do is I can continue to do my division, or look at the polynomial that I just got out. x squared minus 7x plus 12. Well, hopefully we look at this and we think that, hey, I can factor this. That would be a good thing for us because I can continue to break this down, and factoring is a little bit easier than synthetic division because I find multiple roots at the same time. So because this is a quadratic, I know I'm going to set up with two factors. They're both going to start with x and x because our first value is a 1x squared. And now we're going to use that diamond math method. I need two numbers that multiply to 12 and add to negative 7. Hopefully we notice those are going to be a negative 3 and a negative 4. So I first broke off or divided out an x minus 1, which I found out went in evenly. So this is one of my factors. I was left with this polynomial, which I can then factor again. So therefore, my factors are going to be that x minus 1 I found through division, and then the x minus 3 and x minus 4 that I got from factoring once I divided my original polynomial by x minus 1. This is the factored form of our original polynomial. Now to find the roots, all I would have to do is set each one of those factors equal to 0, which gives me x equals 1, 3, and 4. This is important for us for a lot of reasons. So we couldn't factor in the beginning, but we were still able to find the factors, and therefore the roots, which could then lead us to our x-intercepts, which we can use to graph. So we've got an x-intercept at 1, at 3, and then at 4. Looking at our end behavior, I can see we've got an odd degree, so our end behavior is going to be opposite. It's going to be down to the left and up to the right. And then I can see that each of these factors has a multiplicity of 1, which is odd. So that tells me I'm going to pass right through each one of these x-intercepts. And this is roughly what the graph of our original polynomial is going to be. Let's take a look at another example. So it says, find the zeros. Again, zeros is another word for roots of g of x equals 4x to the fourth minus a 4x to the third minus 19x squared minus 2x plus 6. So I want to find those zeros. To do that, I'm going to need our factors. And I can't factor this. There are 1, 2, 3, 4, 5 terms. We don't know how to factor with 5 terms. So this is exactly when our rational root theorem comes into handy. Now, what I can do is, again, take my p-value, which is 6, and I'm going to list out all the factors. 1, 2, 3, and 6. Then I'm going to take my q-value, which in this case is my leading coefficient, which it always is, but is 4. Well, this one's going to be a little bit more complicated because 4 has multiple factors, 1, 2, and 4. So my list of p over q values is going to be plus or minus all of the factors of 6 divided by all of the factors of 4. So I could do 1 divided by 1, 2 divided by 1, 3 divided by 1, and then 6 divided by 1. But then I'm also going to need to do 1 over 2, 2 over 2, 3 over 2, and 6 over 2. Well, 2 over 2 is 1, which we already have, so I don't need repeats in this list. And then 6 over 2 is 3, and I already have 3 in my list. Now I'm going to continue on and do the same thing with 4. I have 1 over 4, 2 over 4, 3 over 4, and 6 over 4. Well, that 6 over 4 is really 3 over 2. And I can see that I already have a 2 over 4, which is a 1/2. And then I already have a 3 over 2. All right, so this is the list of p over q values. That tells me if there are any real rational roots, they are going to come from this list. Positive and negative 1, positive and negative 2, positive and negative 3, positive and negative 6, positive and negative 1/2, positive and negative 3 over 2, positive and negative 1 over 4, and then positive and negative 3 over 4. Using only what we have right now, I can go ahead and pick a value and try to do my synthetic division. So I'm going to start with 1, and what that means is I am checking to see if x minus 1 is going to be a factor. So I do my synthetic division pretty quickly. and I see that we end up with a negative 15. What that means is we have a remainder, and therefore 1 is not a solution. So x minus 1 is not a factor because it doesn't go in evenly. So this is when the tricky part with using our P over Q values only is a little bit difficult, because I could try a lot of numbers here until I find some factors that work. So what we tell our students is we're going to cheat a little bit. We're going to take a look at what the graph of this looks like and find some x-intercepts, which will tell us what our zeros are. So I did that off to the side here. And what that tells us is I can first see that 1/2 is going to be a solution. So let me put a 1/2 here. And I'm going to do synthetic division with 1/2. So I've got 4, -4, -19, -2, and 6. So I'll drop my 4. We get a 2. I add going down. I get a -2. We get a -1. I add going down. We get a -20. I get a -10. I add going down. Get a -12. And I end up with a -6. And when I add those, they cancel. So what that tells me is x minus 1/2. Sometimes you'll see this as a 2x minus 1 is a factor, which is great. We've got one of our factors, which will lead us to our zeros eventually. So I divided this original polynomial by this factor. That left me with this polynomial. So I can continue to break this down. I could go ahead and try to factor once again. But you know what? I'm just going to keep doing synthetic division, because synthetic division is relatively straightforward for a lot of us. So I'm going to pick another value that I took a look at when I graphed this. And when I graphed this, I got a -1.5, or a -3/2. And that is in our list of P over Q values, just like 1/2 was. So that's why this P over Q list is beneficial. It gives us all the possibilities. Now, all of them aren't going to work, and we kind of saw that over here when we tried one, but it gives us a place to start. So I'm going to go ahead and do my synthetic division. Drop the 4. We're going to multiply by a -3/2 to get a -6, and add going down -8. We get a +12, which is a -8, and then a +12 again, which worked. So now what I'm going to want to do is rewrite my solution of x equals -3/2 as a factor, just kind of like what we did previously over here. So as a factor, that's going to be x plus 3/2, or we could write that as 2x plus 3. All right, now we would continue this process where, again, I could take a look at my graph and see if there are any nice rational roots that I could get from this list and do my division with to simplify. But what we might notice is I end up with 4x squared minus 8x minus 8 after I divided out my two factors. What we have here is a quadratic, which we can typically solve or factor quadratics. So if I start to factor this, I divide out what they have in common, and I end up with this quadratic, x squared minus 2x minus 2. Unfortunately, that is not factorable. So down here, when I'm writing the factored form of my polynomial, I'm going to have my first factor, which was, what do we do? 2x minus 1, so I'm just choosing this one. And then I have 2x plus 3. And now I will have my 4 in front, which I just got from here. And then I will have x squared minus 2x minus 2. This is the factored form of my original polynomial, because this is as far as I can get in terms of factoring. But we got to remember that I also want to find my roots or my solutions. So I actually am going to want to solve this quadratic over here. So what I'm going to do is I will copy this and I'll paste it over here so we can find our other solutions. So because this is a quadratic, I can try to factor, which we've already done. I can use inverse operations, that means taking the square root, or I could use quadratic formula. Because I'm in standard form, I'm going to use quadratic formula. So x will equal the opposite of b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. So I'll end up with x equals 2 plus or minus the square root of, we'll have 4 plus 8, which is 12 over 2. And if we recall, the square root of 12 can be split into the square root of 4 and the square root of 3. So I'll have x equals 2 plus or minus the square root of 4 is 2 with the root 3 over 2. And I can actually do one more step where I divide both of these values by 2. So if I notice that these numbers all have a GCF, I can go ahead and divide that out or simplify my fraction to get x equals 1 plus or minus 1 root 3 as my other two solutions. And again, this is a quadratic, so I should end up with two solutions, which I have. So my roots here are going to be the solutions I found before, which include x equals 1/2, x equals -3 over 2, and those I found using my rational root theorem and synthetic division to confirm right here. And then I also just got 1 plus the square root of 3 and then 1 minus the square root of 3, which is going to be our solutions as well. So just like we would kind of assume here, because I have a degree of 4, I end up with 4 solutions or 4 roots. All right, so this is just kind of a recap of what we've done so far. The rational root theorem allows us to get possible roots that we wouldn't otherwise get. And the reason I say that is because if you look back to this problem, so far all we have to find our solutions or our roots is to factor. And we're unable to factor this. So the rational root theorem gives us another path we could take. We get a list of potential real rational solutions that we can then do synthetic division with to confirm if it goes in evenly. If it goes in evenly, we get factors and we get roots. All right, we are doing that so we can eventually continue to break down or divide out our different factors so we can find all factors that multiply to give us our original polynomial. All right, in some of these situations, we only need to do synthetic division one time to get to a polynomial we know how to either factor or, if it's not factorable, solve on our own. And so that was the case here. Technically, what we could have done is we could have continued to do synthetic division and looked at our graph to find other possible roots from this list here and just continued to do synthetic division if we wanted to until we ended up with nothing remaining. And that would have given us all of our roots as well. But I chose the route of factoring the quadratic we got out because I was able to get to 2 factors at the same time as opposed to just one when we do division. All right, so we essentially are going to take our factors of p and divide by the factors of q, and we are going to get a list of potential rational roots. What we can do is use synthetic division to go ahead and divide different values out until we find something that works. We're going to use a little bit of, our tools to help us here, and we're going to peek at the graph so we know what numbers we should be doing division with. And just as a quick reminder, if I graph x cubed minus 8x squared, x cubed minus 8x squared plus 19x minus 12, we can see that I'm getting my rational roots from my x-intercepts. So the 1 is what I started with right here. That's how I knew to start synthetic division with 1. And then we can kind of go from there. I could have used 3 or I could have used 4. So we essentially look at the graph to figure out where we should start our synthetic division so we can start to break apart our original polynomial down into its factored form, because that helps us find our roots. This is another example here, but the only difference is I had to do synthetic division several times before I got to a polynomial. I knew how to find the remaining factors on my own. And what ended up happening is it actually wasn't factorable. So I had to take the factors I was able to find in the remaining portion to list out my factored form. And then to find my roots, I took the part that I was unable to factor and I solved it to find my remaining values of 1 plus the square root of 3 and 1 minus the square root of 3. All right, as always, thank you for listening. If you have any questions or concerns, please feel free to reach out.